Thank you. The image is stretched, but okay, I will continue if you can change during the presentation. It's okay. So I'm Aina. I will present. So I will talk about the potential of carpooling for reducing how much distance we travel by car. I'm a PhD student in third year in Grenoble. So I will start with a bit of context. In France, the transport sector, among the other, represents 1/3 of the total GHG emissions in the territory. And in the French National Low Carbon Strategy, that is the SNBC in French, which is the official strategy to reach the goal fixed by the Paris Agreement. In this strategy, we plan to reach a quasi-decarbonation in 2050. To do this, one part of the strategy is the carpooling for the local mobility. So we can read it in the official strategy, but also in some technical documents that support this strategy. Here we can see that there is even a goal of reaching 1.75 person per vehicle before 2050. And in practice, you can see that, for example, this year, there is an incentive for participating in one of the digital carpooling platform here. So it's really targeted to improving the role of digital carpooling platform. This goal of person per vehicle has been derived for the Grenoble local transportation plan. So we are in Rennes here, as you know. Grenoble is here in the French Alpes. And there the objective is to reach an average occupancy rate of 1.4 for the commute flows between the metropolis center and the countryside. So the flow with a road there. And if I want to express that in goals of vehicle kilometer traveled, so we say VKT, that means reducing the distance traveled by 24%. So that leads to our research question: can daily carpooling help meet the vehicle occupancy goal targeted by this plan in Grenoble? In other words, can ICT, through the digital carpooling platform, help meet this goal? We try to answer this with three contributions. First, the methodology to evaluate a potential for the daily carpooling for reducing VKT. Then an open source tool implementing this methodology, and an estimate for this potential in the Grenoble area. So roughly speaking, we generate, so to do our approach is generating first population with the associated travel demand, and then make this population carpooling. Assess how much avoided VKT we can get through the carpooling in this synthetic population. So the first step, just to detail a bit, we want a population with the schedule for each synthetic inhabitant and for an average working day. The challenge here is to be consistent with the data in input that are open and public survey results. And for the second stage that is computing the carpooling scenario, so we want to do this by maximizing the avoided VKT and taking into account the schedules of the synthetic population for each traveler. For example, if I go from home to work at the morning by carpooling, I cannot take my car for returning back to home. So we do that, for example, by tracking the vehicle location. The challenge here is the scalability, but I won't detail this today. So there are more details in the paper, or you can ask questions also. The advantage of our approach is the genericity. So in particular, we can handle different carpooling schemes, and it is easily adaptable to other areas in France. So about area in France. So as I said before, I focus on the Grenoble area. So on the left, this is all the synthetic trips we can get with the software. So this is an area that is greater than 6,000 kilometers square with a population of more than 600,000 people. And for them, we compute carpooling teams by gathering solo driver and by preserving people's schedules, which we make them carpooling for two carpooling schemes in this case study. The first one is the identical carpooling scheme. We call it the scheme where people can carpool together if the origin are the same or almost the same, close enough, we said, and the destination are also close enough, and the inclusive carpooling where people can be picked up or dropped off along the path of a driver path. So I said closed enough. That means two parameters we have to fix that are the time constraint and the space constraint. So that means how much flexibility I have in my schedules or around my home or workplace to get to a carpooling vehicle. And we have two other parameters that are the vehicle capacity, so the number of passengers that can go into a vehicle, so plus the driver, that is also someone who want to go to work or to home, and an adoption rate. By this parameter, we wanted to model the fact that not everybody participates into a carpooling service. So this is the number of solo drivers that we want to participate. This is a parameter between 0 and 100%. So these are the all kind of results we can get if we vary each of the parameters. I won't detail this either, but I will focus on one scenario for one parameter, that is the effect of the adoption rate on the selected commute flow I spoke about just before. So the commute flow are the one between the metropolis and the countryside. On this graph, you can see on the x-axis, so the adoption rate between 0 and 100%, and on the y-axis, there is the avoided vacancy on the left in million of kilometers, and on the right as a share in percentage of the commuter flow, of the commuting VKT. And the other parameters are fixed with very optimistic settings. So this is the maximum settings we can get to have a sort of maximization. And just if you remind, there is this occupancy goal. It is equivalent to avoid 24% of the commute VKT. And if you look on the figure, that means that more than 55% of the current commuter need to participate in the carpooling service to reach this avoided commute VKT goal. And that is a lot. That means that if based only on daily carpooling of the solo driver, meeting this goal means fast and massive change. If you remember, this is before 2030. So we have still some limitations. Uncertainties are dependent on the travel demand synthesis. So we still need to check that. And we'll also consider a fixed travel demand, whereas carpooling can influence mobility a bit. So I can I could change my schedule to match other people's schedule to be able to carpool. And the travel demand will probably evolve by 2050. So we didn't take this into account. So for the future work, we need to consolidate the methodology by checking, as I just said, the travel demand synthesis, the uncertainties, with respect to the carpooling analysis, compare the result with other types of model, sort of validation of our model, and we also want to broaden the scope of the study. So comparing the potential of the carpooling with other levers, like modal shift to bike and public transportation. We already have some result on this, so we can say, this is preliminary result, but from this we can see that I think half of carpoolable trip can be done by bike, for example, just to see. And also another future work is that we want to study the effect of the evolution of the travel demand on our model and our results. So thank you for listening.